Welcome back to our series on dynamic topology. In this session, we're jumping right into a really foundational concept from Wyburn's text, something called complete spaces.
So to get started, let's think about a little puzzle. Imagine you're following a trail of points, and each point is getting closer and closer to the last one. You can see they're all bunching up, they're heading towards a very specific destination. But what if, when you get right to where that destination should be, it's just not there? It's like a hole in your space. How do we even deal with that mathematically?
A classic, perfect example of this is the space of rational numbers, all the fractions. It's super easy to create a sequence of rational numbers like 1, then 1.4, then 1.41, 1.414, and so on, that gets closer and closer and closer to the square root of 2. The terms are clearly wandering towards something. But the destination, the square root of 2, well, that's an irrational number. It's literally a hole in the fabric of the rational numbers.
Now, this whole problem of holes is a really big deal in topology and analysis. So, of course, mathematicians came up with some seriously powerful tools to handle it. And this brings us right to the heart of today's explainer: Cauchy sequences and complete spaces.
Okay, first things first, we need a formal way to talk about a sequence that's bunching up, and we call that a Cauchy sequence. The really brilliant insight here is that a Cauchy sequence doesn't actually care about a limit point. All it cares about is that the terms of the sequence are getting infinitely close to each other. It's a way of looking at a sequence and saying, hey, this thing should converge, just based on its own internal behavior. And that leads us to the solution, a complete space. A complete space is a space that basically fulfills the promise of every single one of its Cauchy sequences. If a sequence looks like it should converge, it does converge. And, this is the crucial part, its limit is right there, inside the space. No missing points, no holes. It's complete. So, let's circle back to our original example. The rational numbers, which we call Q, are incomplete. They're full of these Cauchy sequences that point to destinations like the square root of 2, or pi, numbers that just aren't rational themselves. The real numbers on the other hand, are the complete package. I mean, they were pretty much constructed specifically to fill in all those gaps, making sure every single Cauchy sequence finds a home. Okay, so we've got a handle on what a complete space is, but why does it matter so much? Well, it's because completeness isn't just some neat label. It's a structural guarantee that unlocks other incredibly powerful properties. And one of the most important is its deep, deep connection to compactness. And here it is. This is a beautiful, incredibly useful theorem right from the text. It says that if a metric space has two key properties, it's guaranteed to be compact. What are they? The first is being totally bounded, which just means you can cover the whole space with a finite number of small regions. And the second? You guessed it, it has to be complete. You put those two together and bam, you get compactness. This is a really big deal in analysis. The logic here is just so elegant. You start with any infinite set. Because the space is totally bounded, you can keep zooming in and trapping infinitely many points in smaller and smaller areas. This lets you build a Cauchy sequence. And here's the magic step. Because the space is complete, we know for a fact that sequence has a limit inside the space. And that limit point proves our original infinite set has a limit point, which is the very definition of being compact. Completeness is the hero that guarantees our sequence actually lands somewhere. But wait, we're not done. Completeness isn't just about the structure of the space itself. It also gives us some incredible power when we start working with functions that are defined on these spaces. Now, I know this statement looks a little dense and technical, but what it's saying is just profound. It's a powerful guarantee. It says if you have a well-behaved function, one that's uniformly continuous, meaning it doesn't get infinitely steep anywhere, and you've only defined it on a set with holes, the completeness of your target space lets you extend that function in exactly one way. Let's just break that down a bit. Think of it like this. Say you've defined a function on just the rational numbers, so you know its value at every single fraction. But what about its value at the square root of 2? This theorem tells us that if the space you're mapping to is complete, there is a single, unique, and continuous way to fill in that blank. The completeness of the target space just gets rid of any ambiguity and lets you perfectly patch all the holes in your function's domain. Pretty cool, right? All right, let's pull all these threads together. We started with a pretty simple problem, sequences that head towards a hole, and we ended up with a solution that unlocks some seriously deep and useful properties in topology.
So if you're going to take away anything from this, here are the big ideas. A complete space is a metric space with no holes, where every Cauchy sequence actually converges. This property, when you combine it with total boundedness, gives you compactness. And it's the secret ingredient that lets us uniquely extend functions. It's a concept that really brings a sense of certainty and solid structure to our mathematical world. And to leave you with a final thought to chew on, something exercise 6 in the text hints at. All of our examples have been about spaces of points, like the real numbers. But what if you built a space where each point was actually an entire function? I mean, can a space of functions be complete? And if it can, what does a converging sequence of functions even look like? That's a huge topic for another day, but it just goes to show how powerful and incredibly far-reaching this idea of completeness really is.